Hey folks, welcome to another set of Chemistry 2 video notes. In today's lesson, we're going to be covering Chapter 10, Electron Transfer in Reactions. By the end of this lesson, you should have a basic understanding of electricity and chemistry, oxidation states, and oxidation-reduction reactions. Let's get started. First off, just what is electricity? Electricity is basically just moving electrons, usually through a wire. When we talk about electricity, we often discuss the voltage and the current. The voltage is what's pushing those electrons through the wire, and the current is just the flow of those electrons. If you think about it like a squirt gun, the voltage would be whatever pressure you've built up inside of the tank by pumping air into it, and the current would be how fast the water shoots out the nozzle of the squirt gun. Together, they help us describe our electricity and determine what it can be used for. Too much current can cause devices to be overloaded and get too hot. Not enough will cause them to slow down and be less effective, like your phone when the battery's on its last leg. One of the types of electricity that we encounter every day is called alternating current, and it's produced by electrical power plants. In these power plants, a turbine is often powered by steam to get it to turn. As it turns, it causes a rotor with coils of copper wire on it to rotate between two magnets. As it does this, the magnets cause the electrons in the copper wire to flow back and forth, producing our alternating current. The other type of electricity that we encounter daily is called direct current, and we get those from batteries. These batteries contain chemicals that allow electrons to be transferred or flow from one chemical to the other. The batteries eventually die because all the electrons that will transfer get transferred. So there's no more left to continue the series of electron transfer reactions that produce that direct current electricity. While alternating current is incredibly cool and useful, we're going to focus on those electron transfer reactions that produce the direct current we see in batteries. As you might guess, an electron transfer reaction involves a transfer of valence electrons. If we see that a particular element on the reactant side of an equation has a different charge on the product side, that's a bright neon sign of a clue telling us that an electron transfer reaction must have taken place. In order to understand how these electron transfer reactions occur, we've got to understand how to assign oxidation states. Oxidation states are just positive, negative, or neutral numbers that we give to atoms in a molecule or compound based on how many electrons we assign to those atoms. It's kind of similar to how we count up electrons around each atom when drawing Lewis structures to make sure that each atom has 8 electrons around it. But in this time, we don't count the electrons in a bond for 2 different atoms. It's even more similar to how we assign formal charges on our Lewis structures. As you might remember, to assign formal charges, we take the number of valence electrons the atom has on its own and subtract 2 for each lone pair on that atom, and 1 for each bond, since the 2 electrons in the bond are shared between the 2 atoms. In other words, we basically just took those 2 electrons in a bond, gave one to one atom, and gave the other to the other atom. Oxidation states are found in the exact same way, except instead of always evenly splitting those shared electrons between 2 atoms, counting a bond as just 1 electron for each atom, we're going to count the bond as 2 electrons. But we're only going to count them for the atom that is more electronegative. If the 2 atoms in the bond happen to have the same electronegativity, then we determine the oxidation state the same exact way we do formal charges by splitting those 2 electrons evenly between those 2 atoms. If we can draw the Lewis dot structure and look up electronegativities, assigning oxidation states should be very easy. For instance, the Lewis dot structure for water looks like this. We know that oxygen is way more electronegative than hydrogen, so the pairs of bonding electrons between the oxygen and the hydrogen atoms will be assigned only to the oxygen atom. Oxygen normally has 6 valence electrons, and we just assigned 8 electrons to it. So 6 minus 8 is -2. In this molecule, oxygen has an oxidation state of -2. The hydrogens, which normally come with 1 valence electron, are assigned 0 electrons. So 1 minus 0 gives hydrogen an oxidation state of +1. As long as you can draw those Lewis dot structures correctly and look at an electronegativity chart while doing this, This electron bookkeeping method is a completely foolproof way to assign oxidation states. On the other hand, assigning oxidation states with that method takes a lot longer than the shortcut method that most people use once they're ready to move on from concept to practice. If you're dealing with ionic compounds and you know the charges of each ion, then those charges are your oxidation states. Otherwise, you've got to do a little bit of work to find the oxidation states, like for each element in a polyatomic ion or in a covalent molecule. There are 4 major rules with a couple of exceptions. Number 1, any substance that's in its elemental state, that is not an ion but all by itself, has an oxidation state of 0. This includes our Brinkelhoff elements like Br2, I2, N2, etc. Rule number 2, we already said if you know the charge of a single element ion, you know its oxidation state. Rule number 3 comes in 3 parts with a few exceptions. Hydrogen has such a low electronegativity that it's almost always +1, except when bonded with a metal, which usually has an even lower electronegativity. In that case, the hydrogen gets an oxidation state of -1, and the metal gets the oxidation state that is positive. Oxygen is almost always -2 because it has such a high electronegativity. The only time this isn't true is when it's bonded to fluorine, which is the only element with a higher electronegativity, or to itself in a peroxide like H2O2. And for the third part of Rule 3, halogens are almost always -1. Fluorine is the most electronegative element, so it's always -1, no exceptions. Chlorine, bromine, and iodine are usually -1 unless they happen to be bonded with an atom that has a higher electronegativity. Lastly, and possibly most importantly, the sum of all oxidation numbers for all atoms in a molecule has to add up to 0. Or if it's a polyatomic ion, the sum has to equal the polyatomic ion's charge. The general concept is that if your oxidation state is positive, it has fewer electrons assigned to it than it would have had in its elemental state. And if it's negative, it's got more electrons assigned to it than it would have had in its elemental state. I won't be picky about it, but FYI, if we wanted to make sure we're writing oxidation numbers properly, we write them with the positive or negative sign first, then the number. The other way around is how we write charge. You might have noticed me writing charges as 2+ or 3- or whatever before, as opposed to +2 and -3. That's why. Here's a couple of quick examples. For CHBr3, we could draw out the whole Lewis dot structure. After we've got that drawn correctly, we can count how many electrons get assigned to each atom. Remember, lone pairs automatically belong to the atom they're with. Shared electrons go toward the atom with a higher electronegativity. Bromine has a higher electronegativity than carbon, so all of the electrons that are shared between carbon and any bromine get assigned to the bromine. Carbon has a slightly higher electronegativity than hydrogen, so the 2 electrons between carbon and hydrogen get assigned to the carbon atom. Now, we go through and take the normal number of valence electrons that each atom has, 7 for bromine, 4 for carbon, and 1 for hydrogen, and subtract the number of electrons assigned to that atom. So, for all 3 bromine atoms, we'll take 7 minus 8 and find that their oxidation state are all -1 in this compound. Carbon would be 4 minus 2, giving it an oxidation state of +2. Lastly, hydrogen would be 1 minus 0 for an oxidation state of +1. If you add all of those up, -1, -1, -1, +1, and +2, the total is 0, as it should be. If you want to use the shortcut method, we'd look at our shortcut rules. There's no rule for carbon, so we can't figure that out quite yet. Hydrogen is always +1 unless it's bonded to a metal, and there's no metal here. Bromine is -1 unless bonded to an atom with a higher electronegativity, and it's not. So we know the overall sum has to equal 0, and we have 3 -1s and 1 +1. Currently, our overall sum is -2, which means the carbon has to be +2 to cancel that out. C2H4O2 is another great example. Cut that piece out and glue it in your notebook here, then leave some space in your notes and try it out on your own. We'll go over the answer together in class, so when we do that, make sure you've got it right. If you have it correct and written in your notes, you'll probably get some extra credit points for that. Now that we know how to assign oxidation states, we can use them for something practical, recognizing when an electron transfer reaction occurs. You'd go through and assign oxidation states to every element in the balanced equation. If you see that any element changes its oxidation state from one side of the equation to the other, then you know an electron transfer reaction must have occurred. Electron transfer reactions are also known as oxidation-reduction reactions, or redox for short. We call them that because when electrons get transferred, something has to lose electrons and something else has to gain those electrons. When something loses electrons, we say it has been oxidized. When something gains electrons, we say it's been reduced. Those are two very important terms you need to know by heart. A good way to remember this is OIL-RIG, which stands for oxidation is loss, reduction is gain. The commonly confusing part about this is that when you lose electrons, your oxidation number increases because you lost some negative particles. It's backwards from what you'd automatically think if you think of it that way. But if you remember that reduction is gain, when the oxidation state gets reduced or smaller, that means the element gained electrons. Two other terms you need to know are reducing agent and oxidizing agent. Agent here is just another word for helper. So the reducing agent is what helps something else get reduced. In other words, if I'm an atom that loses an electron, another atom will pick up that electron and get reduced. I just helped that atom get reduced, so I'm a reducing agent. You could also say that I got oxidized because I lost an electron. Vice versa, the thing that gains an electron had to take it from somewhere else. So it helped another element to lose its electron or get oxidized, so we called it the oxidizing agent, or the thing that got reduced. In the example here to the right, you can see that oxygen went from 0 to -2, which means it gained electrons or got reduced. It can also be called the oxidizing agent. Carbon loses 8 electrons to go from -4 to +4. This means carbon got oxidized and must have been the reducing agent. Here's another quick example. P4 is in its elemental state, as is Br2. So both of those get assigned oxidation states of 0. Shortcut rules say that halogens are usually -1, so I'm going to call the bromines in phosphorus tribromide -1, which gives us a total of -3 right now. And that means the phosphorus has to be +3 to cancel that out. So phosphorus went from 0 to +3. This means it lost electrons and was oxidized. Bromine went from 0 to -1, so it gained electrons and was reduced. If we set it up correctly, we can create a galvanic cell, or a battery, by taking advantage of this electron transfer flow. To have electricity moving, you've got to have a full and complete circuit. So we take 2 beakers of different solutions and connect them in 2 places, one with a spectator ion salt bridge and the other with a wire. We'll figure out why in a second, but in this setup, zinc is more likely to lose electrons. So the zinc electrode will convert from zinc atoms to zinc 2+ ions. Through this process, electrons will flow from the zinc electrode through the wire to the copper electrode and then latch on to the copper 2+ ions floating around in that beaker. When the electrons latch onto the copper 2+ ions, they form copper atoms onto the electrode. So as this is going on, our copper electrode will gain mass because it's gaining more copper atoms, and the zinc electrode will lose mass because its atoms are turning into ions into solution. Also, as this occurs, we get a net buildup of positive charge on the left beaker and a net loss of positive charge on the right. To balance this out, this is where our neutral salt bridge, something like potassium nitrate, will send its positive ions toward the copper side and its negative ions toward the zinc side. A couple of quick definitions. Any metal strip in which electrons move through in these setups could be referred to generally as an electrode. More specifically, the side that gets reduced, where electrons flow toward, we mark with a positive symbol because the negative electrons are attracted to the positive side. We could also call that electrode a cathode, kind of like a cation. On the other side, where oxidation occurs or loss of electrons occurs, that gets branded with a negative sign and called an anode because it's like an anion and it pushes those electrons away from it. Another good way to remember is that electrons move away from the anode. So we can set up all sorts of galvanic cells and see which way electrons will flow. To do this, you just place one of the metals in a solution of the other metal's ions. The one that's more active will be the one that is more likely to stay as an ion. Between magnesium and zinc, we see that the zinc ions form into atoms on the magnesium strip. This means that magnesium would desire to lose electrons and become a cation more than zinc does. In the second example, we see that copper is more likely to lose its electrons than silver. So silver metal in a copper ion solution does nothing. But copper metal in a silver ion solution converts the silver ions into a nice pretty silvery metal and the copper metal into copper ions. Throughout the last few hundred years, scientists have done these experiments several times and in several different ways, and that's led us to our beautiful, handy-dandy electromotive force series, or what we sometimes call the activity series of metals. Metals, when they react, tend to lose electrons. So we say that the metals that are most likely to lose their electrons, or to be oxidized, are the most active. This is similar to the trend for reactivity on the periodic table, but it doesn't follow it exactly. So I'd use the EMF series or activity series that we're given here. Electrons will always naturally transfer from the more active metal electrode to the less active metal electrode. Lithium is the most active metal. Gold is the least active metal. As we mentioned on the last slide, the copper in that galvanic cell turns from copper ions to copper atoms. You'll see a buildup of copper atoms on the copper electrode. When this happens, we call it plating out, and it's how we get things like gold-plated jewelry. So let's do a couple of examples. For the first one, we're comparing aluminum and mercury. According to our activity series, aluminum is more active than mercury. That means it would prefer to exist as positive ions. So the second option between these two would be the correct one, as the product side has the aluminum existing as ions. Between iron and copper, iron is more active, so the correct answer here is the first one, with iron ions on the product side. Okay, last but not least, an older definition of oxidation basically just meant that something combined with oxygen in a really slow combustion reaction. This is what we know as rusting or corroding. As iron rusts, it goes from an oxidation state of 0 to an oxidation state of positive 3, which means it gets oxidized. This phenomenon is responsible for the once beautiful copper Statue of Liberty with its goldish-brown color forming a nice outer layer of that pastel green-looking copper oxide. Originally, it had an outer copper layer, which on its own will form that green patina. But just under that layer was iron. This was a major issue because iron is more active than copper. If the copper stayed as atoms and didn't get oxidized by the salty seawater and air, things would be fine. But as it turned into copper ions, it then had the ability to steal electrons from the iron, causing the iron to oxidize or rust. This process would reform the copper atoms, then cycle through all those steps again, eventually eating away at all of the structural iron on the inside of the Statue of Liberty. To avoid this on metal ships, it's common to bolt a sacrificial plate of a more active metal onto the ship. When you do this, whatever oxidation occurs will happen at that spot before any oxidation on the ship occurs. It's a lot cheaper to replace a small sacrificial plate on the side of a hull than to repair rusted out holes on the ship. Well, that's all for today, folks. This was a lot of brand new stuff and probably a bit long of a video, but I hope you made it through fine and came out the other side with a little bit more knowledge. As always, if you have any questions, ask.